Hello, in this lecture we find out the area of the green triangle. In the drawing we have a quarter circle, BOA is a quarter circle. Inside the quarter circle we have line segment PQ that is equal to 3 units, line segment AQ equals to 5 units in its length, and this angle APQ equals to 90 degrees. Our mission is to find out the area of this green right triangle AOQ. So first of all we focus on the right triangle APQ. The right yellow triangle APQ, and we'll implement on this right triangle the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, the hypotenuse in the right yellow triangle APQ is AQ, therefore the square of the hypotenuse is AQ squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to PQ squared plus AP squared. Repeat again, according to the Pythagoras theorem, here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the right triangle APQ equals to AQ square. AQ square equals to PQ square plus AP square. So AQ is 5, therefore AQ square is 5 squared, that is 25. And it is equal to PQ square. PQ is 3, therefore PQ square is 3 squared, that is 9. Plus AP square. AP is unknown, so we leave this it is. In conclusion, we found out that according to the Pythagoras theorem, 25 equals to 9 plus AP square. We subtract 9 from this equation, and we get that 25 times 9 is 16, and 16 equals to AP square. We take out of this equation, and finally we found out that AP equals to the square root of 16, that is 4. AP equals to 4 units in its length. So I write it down in the original drawing that AP equals to 4 units in its length. Here we have a quarter circle. A or B is a quarter circle, and you can easily complete the quarter circle to a circle, and then point O will be the center of the circle. And you have the rule that if you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. Repeat again on rule number 2. According to rule number 2, a perpendicular from the center of the circle towards any chord bisects the chord. The center of the circle is here at point O, so if you draw a perpendicular towards chord BC, so this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as M. So according to rule number 2, the perpendicular the perpendicular OM bisects chord BC. So the first half will be BM and the second half will be MC. Or BM equals to MC. So whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. In this case, the perpendicular OM from the center of the circle bisects chord BC, therefore BM equals to MC. We can implement rule number 2 in our drawing. From the center of this of the circle, that is to say from point O, we will draw perpendicular on chord PA. So this angle equals to 90 degrees, and this angle it is also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and PA as M. And according to rule number 2, the perpendicular OM from the center of the circle, that is to say from point O, bisects chord PA. So we divide this into two halves. PA equals to 4. And OM divides PA, so the first half will be PM, that is 2, and the second half will be showing line segment MA, that is also will be equal to 2 units. We define the intersection point between perpendicular MO and line segment AQ as N. We define this angle AM and as theta. If we focus on this right yellow triangle AMN, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Likewise, if you focus on the big right yellow triangle APQ, in this big yellow triangle APQ, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. In the next step, we'll prove that the small right triangle AMN is similar to the big right triangle APQ. Okay, so the big triangle APQ is similar to the small triangle AMN. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So I write it down, angle APQ in the big triangle, this angle equals to this angle, that is angle AMN in the small triangle, they are both equal to 90 degrees, therefore they are equal to each other. Repeat again. Angle APQ in the big triangle equals to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta belongs to triangle AMN, and also belongs to the big triangle APQ. That is to say, it is a common angle that belongs to both triangles. So you can write down that angle theta equals to itself. Okay, and we'll call angle theta two different names in order to emphasize that it belongs to both triangles. So angle theta that belongs to the big triangle APQ is angle PAQ. And it is equal to angle theta itself. Angle theta that belongs to the small triangle, it will be called angle MAN. I'll repeat again. Angle theta that belongs to the big triangle, it is called angle PQ, and it is equal to angle theta itself that belongs to the small triangle. Then it is called angle MNA. This is angle theta. So angle theta is a common angle that belongs to both triangles. Therefore, angle theta equals to itself. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So this angle in the big triangle is angle PQA, and it is equal to this angle in the small triangle, that is actually angle MNA. And it is equal to 90 degrees minus theta. Both angles are equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the triangles in the big right triangles are correspondingly equal to all the triangles in the small right triangle. Therefore we proved that those two right triangles are similar to each other according to angle similarity rule. Okay. So the big triangle APQ is similar, this is the sign of similar, to the small triangle AMN according to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle are correspondingly equal to all the three angles in another triangle, then you actually proved that those two triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will conclude that the following relationship exists between their sides. That PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is equal to QA in the big triangle over NA in the small triangle. So I write it down. PA in the big triangle over MA in the small triangle is equal to PQ in the big triangle over MN in the small triangle, and it is equal to QA in the big triangle over NA in the small triangle. Repeat again. PA over MA equals to PQ over MN equals to QA over AN. PA equals to 4 units over MA equals to 2 units. MA equals to 2 units. And it is equal to PQ. PQ is 3 units. Over MN is unknown, so we leave it as it is. And it is equal to QA. QA equals to 5 units according to what is given us the question. Over NA. In conclusion, we found out that 4 over 2 equals to 3 over MN equals to 5 over AN. From this equation, we will conclude that 4 over 2 equals to 3 over MN. Four over 2 is 2. So 2 equals to 3 over MN. We'll multiply this equation by MN. And we get that 2 times MN equals to 3. We'll divide this equation by 2 and finally we'll get that Mn equals to 3 over 2. 3 over 2 is 1.5. So we found out that the length of line segment Mn is 1.5 units. So write it down, that line segment Mn equals to 1.5 units in its length. This line segment Mn equals to 1.5 units in its length. From the same equation, from this equation, we also can conclude that 4 over 2 equals to 5 over NA. Again, 4 over 2 equals to 5 over NA. So I write it down. 4 over 2 equals to 5 over NA. 4 over 2 is 2, so 2 equals to 5 over NA. We will multiply this equation by NA, and finally we will get that 2 times NA equals to 5. We'll divide this equation by 2, and finally we will get that NA equals to 5 over 2, that is 2.5 units. So line segment NA equals to 2.5 units in its length. I write it down in the original drawing. And the length of this line segment NA is 2.5 units. And what is the length of line segment QN? This line segment QN. From knowing it is very easy to see that QN equals to QA minus NA. Again, QA minus NA equals to QN. I write it down. QN equals to QA minus NA. Again, QN equals to QA minus NA. So QN equals to QA. QA is 5. And we just right now found out that NA equals to 2.5. Yeah, NA equals to 2.5. 5 minus 2.5 is 2.5. So we found out finally that Qn equals to 2.5 units. So I write it down in the original drawing. Qn equals to 2.5 units. This line segment Qn equals to 2.5 units in its length. We know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle. Therefore, we'll block this right green triangle AQO in a circle. So I copy this green triangle in a new page and we will block it by a circle. So actually, this is the right green triangle AQO with the copy from the original drawing. Now we will block this right triangle by a circle. So inside this circle, we have peripheral angle AOQ that is equal to 90 degrees. Peripheral angle AOQ equals to 90 degrees in its size. And we also have rule number 5 that says that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. I'm repeating again. According to rule number 5, any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Here, this peripheral angle ABC is equal to 90 degrees, therefore it rests on the diameter of the circle, that is to say AC is the diameter of the circle. Okay? And the center of the circle is the point O. So AC is the diameter of the circle. So we can actually implement rule number 5 in our drawing. Because of the fact that peripheral angle AOQ is equal to 90 degrees, it must rest on the diameter of the circle. That is to say, QA is the diameter of the circle. QA is the diameter of the circle. And we also know that the diameter of any circle is 2 times the radius. So the diameter of our circle will be 2 times the radius, 2 times r. From one side, but from the other side, it is given us the equation that QA equals to 5 units in its length. And from this equation, we derive that 5 equals to 2r. Again, 5 equals to 2r. We divide this equation by 2 and finally we will get that r equals to 2.5 units. R equals to 2.5 units. So we found out that the radius of this circle equals to 2.5 units. Okay. In the next step, I will copy. So this is the right triangle AQO. This is also the same right triangle AQO that I copy to. I copy this right triangle here. So we can copy point N from this right triangle AQO to our drawing. So this will be point N that I copy from the original drawing. I found out that AN equals to 2.5 units in its length. And we also found out that NQ it is also equals to 2.5 units in its length. AN equals to 2.5 units. But the radius also equals to 2.5 units. And AN is located on the QOA, that is the diameter of the circle. Therefore, AN must be also the radius of the circle. Likewise, NQ it is equal to 2.5 units, but the radius also equals to 2.5 units. Therefore, NQ must be the radius of the circle. Why? Because actually it is located on the diameter, diameter QA. QA equals to 5 units. QA 5 over 2 is 2.5. So the middle of the diameter QA will be at this point. At this point that actually divides the diameter QA into two halves. The first half equals to 2.5 and the second half also equals to 2.5 units. Therefore, point N is the middle of the diameter. And the middle of the diameter is also the center of the circle. So point N is the center of the circle. Also, we can say that because of the fact that QA is the diameter of the circle, QN is the radius and AN is also the radius. And the center of any circle, if the diameter is QA and QN is the radius and AN is also the radius, the touching point must be the center of the circle. Where is the touching point? The touching point of the two radii is at point N. That is another reason that point N is the center of the circle. So point N is the center of the circle. We join points N and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from point N, that is the center of the circle, and ends at point O, that is the point of the circle itself. This is exactly the definition of a radius. Therefore, NO is the radius of this circle, that is equal to 2.5 units. So you can write down here that NO equals to, line segment NO equals to, is the radius of the circle, that is equal to 2.5 units in its length. In the next step, I will copy the right triangle AMO in a new page and we will implement on this right triangle the Pythagoras theorem. Side AM equals to 2 units since length. What is the length of side MO, triangle AMO? From the drawing, it is very easy to see that the length of MO is MN plus NO. Again, MO equals to MN plus NO. MN equals to 1.5. NO equals to 2.5, so in total MO equals to 1.5 plus 2.5, that is 4. So we have, this is triangle AMO. Again, this is triangle AMO that I copied from the original drawing. So by PT, by Pythagoras theorem, we get that AO squared equals to MO squared plus MA square. Again, the right triangle AO square equals to MO square plus MA square. So AO square equals to MO square. MO is 4, therefore MO square is 4 squared, that is 16, plus MA square. MA is 2, therefore MA square is 2 squared, that is 4. So AO square equals to 16 plus 4 is 20. Here we will take a root out of this equation and we find out that AO equals to the square root of 20 units. So I write down the original line AO, that AO equals to the square root of 20 units here. AO equals to the square root of 20 units. In the next step, I will copy the right grand triangle AQO in a new page and we will implement on this right grand triangle AQO the Pythagoras theorem. AO equals to the square root of 20 units, and the hypotenuse AQ equals to 5 units. So actually, this is the right grand triangle AQO that I copied from the original drawing. According to the Pythagoras theorem, the square of the hypotenuse is AQ squared, and it must be equal to the sum of the sides of the perpendiculars, that is to say it must be equal to AO squared plus QO square. So AQ square, AQ is 5, therefore AQ square is 5 squared, that is 25. That is equal to AO square. AO is square root of 20, therefore AO square is square root of 20 squared, that is 20, plus QO square. Here we subtract 20 from this equation, and we get that 25 minus 20 is 5, so 5 equals to QO square. And we take out of this equation, and finally we get that QO equals to the square root of 5 units. QO equals to the square root of 5 units. Write it down here that QO equals to the square root of 5 units. Now it is very easy to find out the area of the grand triangle AQO. The area of the grand triangle AQO here, the squared bracket is the sign for the area. It means the area of triangle AQO equals to the area of any triangle equals to the base of the triangle times the height to the base. The height must create 90 degrees with the base over 2. So the base of the grand triangle AQO will be QO, and the height to the base is AO. Why AO is the height to the base? Because it creates 90 degrees with the base here. This angle equals to 90 degrees. Repeat again. The base of the grand triangle AQO is QO and the height is AO, all divided by 2. QO equals to the square root of 5 units. and AO equals to the square root of 20 units divided by 2. We have the algebraic identity that the square root of A times square root of B equals to the square root of A times B. According to this algebraic identity, we get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 over 2. 5 times 20 is 100, so inside the root we left with 100 over 2. The square root of 100 is 10, and 10 over 2 is 5. So finally we found out that the area of the green right triangle AQO is equal to 5 square units repeat again. The area of this green right triangle AQO equals to 5 square units. In the next step I will summarize the lecture. In this lecture, we found out the area of the green right triangle AQO. It is given as the equation that line segment PQ equals to 3 units in length, line segment AQ equals to 5 units in length, and this angle APQ equals to 90 degrees, and we have here actually a quarter circle. AOB is a quarter circle. Okay, so here we focused on the right yellow triangle APQ, and we implemented in this right yellow triangle APQ the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the source of the perpendiculars. In the yellow right triangle APQ, the hypotenuse is AQ, therefore the square of the hypotenuse is AQ square, and it must be equal to PQ square plus PA square. Repeat again. AQ square equals to PQ square plus AP square. AQ is 5, therefore AQ square is 5 square, that is 25, and it is equal to PQ square. PQ is 3, therefore PQ square is 3 square, that is 9, plus AP square. So we subtracted 9 from this equation and found out that 25 minus 9 is 16, so 16 equals to AP square. We took out of this equation, and finally we found out that AP equals to the square root of 16, that is 4. So here, line segment PA equals to 4 units in its length. Then here we have AOB is a quarter circle. If you complete the quarter circle to a circle, then point O will be the center of the circle. And we have rule number 2. It says that whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. I repeat on rule number 2. According to rule number 2, a perpendicular from the center of a circle towards any chord bisect the chord. Point O is the center of the circle. From point O, we draw a perpendicular on chord BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to construction. We define the touching point of the perpendicular from point O and BC as M. So according to rule number 2, the perpendicular OM on chord BC bisects chord BC. That is to say, divide this into 2 halves. The first half is BM, and the second half is MC, and of course BM equals to MC. So whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. Here again, the perpendicular OM bisects chord BC, that is to say, BM equals to MC. So we can implement rule number 2 in our drawing. In our drawing, from the center of the circle, that is to say, from point O, we draw perpendicular on AP. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord PA as M. According to number 2, the perpendicular OM from the center of the circle bisects chord PA. that is to say, divide it into two halves. And because of the fact that PA equals to 4 units, it means that the first half will be PM, that is 2, and the second half will be MA, that is also 2. Then we define the intersection point between perpendicular OM and disegment AQSN. We define this angle as theta. So if you focus on the right yellow triangle AMN, this angle equals to theta. This angle was equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees. And 90 degrees plus 90 degrees is 180 degrees, exactly according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, if you focus on the big yellow triangle, big yellow white triangle APQ, inside this triangle, we have this angle, we have that is equal to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Then we proved that the small right triangle AMN is similar to the big right triangle APQ. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. Repeat again. Angle APQ in the big triangle equals to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, angle theta belongs to both triangles. It is a common angle, so angle theta equals to itself. So angle theta can be called as angle PAQ when we see it as belongs to the big triangle, and it is equal to angle theta itself. And when we see it as it belongs to the small triangle, it will be angle MAN. We call two different names to the same angle theta. So angle theta equals to itself. It is a common angle that belongs to both triangles. And finally, those two angles that are both equal to 90 degrees minus theta, therefore they are equal to each other. I repeat again. Angle PQA in the big triangle equals to angle AMNA in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we succeeded to prove that all the three angles in the big triangles are corresponding equal to all the three angles in the small triangle. Therefore, we actually proved that the big triangle APQ is similar. This is the sign of similar to the small triangle ANA according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle are corresponding equal to all the three angles in another triangle, then you actually proved that the two triangles are similar to each other according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. That PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is also equals to QA in the small triangle, in the big triangle, QA in the big triangle over NA in the small triangle. I repeat again. PA over MA equals to PQ over MN equals to QA over N equals to QA over NA. PA is 4, MA is 2, PQ is 3 over MN, QA is 5, and AN is unknown. So I should have found out that 4 over 2 equals to 3 over MN equals to 5 over AN. From this equation we will derive that 4 over 2 equals to 3 over MN. Here 4 over 2 equals to 3 over MN. 4 over 2 is 2, so 2 equals to 3 over MN. We multiplied this equation by Mn and finally found out that 2 times Mn equals to 3. We divided this equation by 2 and finally found out that Mn equals to 3 over 2, that is 1.5. This line segment Mn equals to 1.5 units in its length. From the same equation, we also can conclude that 4 over 2 equals to 5 over An. Here 4 over 2 equals to 5 over An. 4 over 2 is 2, so 2 equals to 5 over An. We multiplied this equation by an, and finally found out that 2 times an equals to 5. Then we divided this equation by 2, and finally found out that an equals to 5 over 2. 5 over 2 is 2.5. So we found out finally that this line segment an equals to 2.5 units in its length. Then what is the length of line segment QN? From the domain it is very easy to see that QN equals to QA minus NA. Again, QA minus NA equals to QN. Repeat again, QN equals to QA minus NA. QA is 5. We just right now found out that NA equals to 2.5. So QN equals to 5 plus 2.5. 5 plus 2.5 is 2.5, of course. So in conclusion, found out that Qn equals to 2.5 units. Here Qn equals to 2.5 units in its length. We also know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle. Therefore, we blocked the right hand triangle AQO by a circle. So this is the right triangle AQO that are copied from the original drawing, and we block this triangle by this circle. Inside this circle we have angle peripheral angle AOQ that is equal to 90 degrees. And we have rule number 5 that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. Again, according to rule number 5, any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Peripheral angle ABC that is equal to 90 degrees rests on AC, that is the diameter of the circle. So we can implement rule number 5 in our drawing. Because of the fact that this peripheral angle AOQ equals to 90 degrees, therefore it must rest on the diameter of the circle. That is to say, QA is the diameter of the circle. QA is the diameter. The diameter of any circle is 2 times the radius. Therefore, the diameter of our circle is 2 times the radius. The radius is r, so it is 2r. From one side, but from the other side, it is given us the equation that QA equals to 5. From this equation, we derive that 5 equals to 2r. We divided this equation by 2 and finally found out that r equals to 5 over 2, that is 2.5 units. So actually found out that the radius of this circle is equal to 2.5 units. Okay, then in the next step I copied point N from the original drawing, this point N, in our original drawing, in our drawing here. This is point N that I copied from the original drawing. Here we have triangle AQO, and here it is the same triangle AQO. So I can copy point N here. It is the same triangle. So AN is 2.5 units, and NQ it is also 2.5 units. Okay. And we know that the middle of the diameter is the center of the circle. If QA equals to 5 units in its length, it is the diameter of the circle. Therefore, the middle of the diameter will be at 0.5 over 2, that is 2.5 units at point N. Because Qn equals to 2.5 and Na it is also equals to 2.5. Okay? And here we have Qn equals to 2.5 units from one side, but from the other side the radius of the circle also equals to 2.5 units, and Qn is located on the diameter. Therefore, Qn that is also equals to 2.5 units must be the radius of the circle. Na equals to 2.5 units, but the radius also equals to 2.5 units. Therefore, Na must be also the radius of the circle. And again, the touching point of the two radii on that are both located on the diameter of the circle, the touching point must be the center of the circle. So we have two reasons that point N is the center of the circle. Why? Because the toward the eye on the diameter, the touching point of the toward the eye is at point N from one side, and the middle of QA is at point N. Why? Because point N bisects the diameter QA and divides it into two halves. The first half is QN, that is equal to 2.5, and the second half is NA, that is also equals to 2.5 units. Therefore, point N must be the center of the circle. Okay, so point N is the center of the circle. Then we join points N and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from point N, that is the center of the circle, and ends at point O, that is the point of the circle itself. This is exactly the definition of a radius. So NO is the radius of the circle, that is equal to 2.5 units. We can write here that NO is the radius of the circle, that is equal to 2.5 units. Then I copied the right triangle AMO in a new page, and we implemented on this right triangle the Pythagoras theorem. Side AM equals to 2 units in its length. What is the length of side MO? From the drawing it is very easy to see that MO equals to MN plus NO. Again, MO equals to MN plus NO. MN equals to 1.5, NO equals to 2.5. Therefore, in total, MO equals to 1.5 plus 2.5, that is 4. So MO equals to 4 units. So actually, this is the right triangle AMO that I copied from the original drawing. My PT is a version from Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse is AO square, must be equal to MO square plus AM square. So AO square equals to MO square. MO is 4, therefore MO square is 4 squared, that is 16, plus MA square. MA is 2, therefore MA square is 2 squared, that is 4. So AO square equals to 16 plus 4, that is 20. We took out of this equation and found out that AO equals to the square root of 20. Here AO equals to the square root of 20. In the next step, I copied the right triangle AQO in the new page, and we implemented in this right triangle AQO the Pythagoras theorem. Side AO equals to the square root of 20 units. The hypotenuse AQ equals to 5 units. This is the right triangle AQO that I copied from the original drawing. According to the Pythagoras theorem, AQ square equals to AO square plus QO square. AQ is 5, therefore AQ square is 5 squared, that is 25, and it is equal to AO square. AO is square root of 20, therefore AO square is square root of 20 squared, that is 20 plus QO square. We subtracted 20 from this equation and found out that 25 minus 20 is 5, so 5 equals to QO square. We took a root out of this equation and finally found out that QO equals to square root of 5 units. Here, QO equals to square root of 5 units. Now it is very easy to find out the area of this great right triangle AQO. The area of this right triangle. The area of any triangle is the base of the triangle times the height to the base over 2. The height must get 90 degrees with the base. So the base is QO and the height is AO. Why the height is AO? Because it creates 90 degrees with the base QO. And the base is QO and the height is AO over 2. QO is square root of 5 units, AO is square root of 20 units, all divided by 2. We have the algebraic identity that the square root of A times square root of B equals to the square root of AB. Therefore, according to this algebraic identity, we will get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 over 2. So inside the brackets, we have 5 times 20, that is 1. Inside the root, we have 5 times 20, that is 100 over 2. The square root of 100 is 10, and 10 over 2 is 5. So in conclusion, found out that the area of this green right triangle AQO equals to 5 square units. Again, the area of this green right triangle AQO equals to 5 square units. Okay, thank you very much.